Hi folks, welcome back to Physics with Captain Rod. I'm making this one to help you out with Unit 2, number 16. So, Timmy and his rocket. Timmy and his toy rocket. Alright, so the first thing I would do with this, you'll notice that Timmy's weight is given in pounds and the rocket also in pounds. The first thing I would do is convert those to newtons. And to do that, you're going to have to look up, how many newtons per pound or how many pounds per newton, either one. Now, once you know the weight of both Timmy and the rocket in newtons, the next thing I would do is figure out the mass of those things, because in any sort of Newton's second law problem, force equals mass times acceleration, you're probably going to need the masses. So, step one here, get the weights of both in newtons. Step two, get the mass of both Timmy and the rocket in kilograms. We're no doubt going to need those. All right, now we can probably start analyzing the problem. And all right, first it says to find the acceleration of the rocket. So what you want to do is draw a free body diagram of the rocket defining our system like this. And I can think of two distinctly different forces on it. We have this rocket thrust force right here, 500,000 newtons. And then the rocket also has a weight. Now, once you have those two forces, and I guess we'll throw air drag out of it, that's pretty well it. Then you can write a force equation to find the acceleration of the rocket. All right, part B, where it says find Timmy's apparent weight while the rocket engine is on. So here's what it means by apparent weight. If you were to stand on a bathroom scale, the scale reads the normal force between your feet, right, and the scale surface. Now, when you're standing in your bathroom and the bathroom's not accelerating, then that normal is equal to your weight, right? But for Timmy, that's not going to be the case. Timmy's accelerating up. So what's going to happen is that normal probably will read a higher value than Timmy's weight. So in that normal, that higher normal, is what I'm referring to when it says find the apparent weight of Timmy while the rocket engine is on. So what you're going to want to do here is draw a free body diagram of Timmy. It should have two forces on it. And then write a Newton's second law equation. And you're looking for the normal force at Timmy's, applied to Timmy's feet. Let's see what else we got here. Oops. Let's see, find the maximum height reached by the rocket if the engines run out after 20 seconds. Okay, so this is kind of going back to Unit 1. And I'll get you started on this. All right, so start with a velocity graph of that rocket. And presumably it started out at 0, 0, meaning at t equals 0, it wasn't moving very fast, or at all. Then the rocket engines fire, and that accelerates the rocket at some number, at some value. And this is a number that you found earlier in the problem. Now, if that acceleration, if we assume it's constant, that's going to give us a linear velocity graph until the rocket runs out of fuel at some time. Actually, that's 20 seconds. Now, this acceleration, remember, you have to say to yourself, how does that relate to this graph? You should be able to, you should hopefully know that, and you should be able to use it to calculate that height. And that height represents the velocity of the rocket the instant the engine shuts off. All right. Now, if you're wondering, well, how do I do that? Well, slope and area. Remember, those graphs have two important properties, slope and area. All right, now after the engines shut off, now the rocket is effectively free falling. But at the instant it shuts off, remember, it's going to have a pretty large positive velocity. But that velocity is going to start decreasing due to gravitational acceleration. And eventually the rocket will get to its highest point in its trajectory there. And at that point, its velocity is pretty close to 0. So this graph is looking like this. And when the velocity is 0, that's here on the graph. And then when the rocket, starts coming downward, now the velocity has changed from up to down. So graphically, we represent with negative numbers now. That's why these are now negative values and increasing in magnitude, because as the rocket falls, it's going to be moving faster and faster and faster. Now, I'll let you folks think about what the maximum height, how it relates to this graph. I think that's probably enough for my input. So I hope that this helps get you rolling on that problem. Have a great day.